everyone, it's Larissa from SMRI Comms. Today I'm chatting to Ivan Guo, who recently visited SMRI as part of the Domestic Visitor Program, and we're having a chat about Ivan's research and what he got up to during his stay.
My area of research is primarily in financial mathematics, so I'm actually a part of the Monash Center for Quantitative Finance and Investment Strategies, which is a research group in the area of financial mathematics. Optimal transport is a very, very old problem originally that came out a couple of hundred years ago. It's motivated by problems in engineering where they need to work out how to transport construction material from one location to another location in an efficient manner. And then over the years, mathematicians and probabilists have come along and further developed the area, and it's found application in a lot of different areas of sciences and economics and computer science. So for example, people use the same sort of techniques to model the origins of the universe. That transition from the Big Bang to the sort of later stages of the universe is in itself kind of like an optimal transport problem where you're transporting material from some initial state to some other state. And then more recently, the example I usually mention is in computer science. People probably have seen all these, digital images of people applying filters to photos, or maybe they've seen these celebrity photos where we try to morph, the face of one celebrity to another. The underlying technique also have a lot to do with optimal transport because they're essentially taking information from a picture and how to sort of efficiently transform it into another picture. In terms of stochastic optimal transport, it's sort of a related area where techniques from probability also are involved in the various analysis techniques. But for me personally, the field of stochastic optimal transport that I'm interested in is its applications in financial mathematics. In particular, you can think about the stock market indices as a random probabilistic distribution. So it's some uncertain quantity that will have a value in the future. And the question of how do you determine how do we evolve from the state it is today? So what is the stock market prices today to what it's going to be in a week, a month, a year? Sort of that process in itself is sort of a transportation problem, and that's very closely related to optimal transport. So the word robust essentially refers to the robustness of your models and calculation with respect to uncertainty within the model. So usually in mathematics or maybe applied mathematics, in order to sort of make any conclusions, you have to first make assumptions about the model that you're working with, about the phenomenon that you're modeling. But what if you have some uncertainty regarding your assumptions? What if your assumptions are wrong by some percentage or in some other way? So the area of robust finance is tackling the question of what is the cost associated to making those errors and what is the worst case sort of scenario within those assumptions. And that sort of, in order to solve those kind of problems, essentially it comes down to a class of optimization problem over the set of potential models. And each model is like a probability distribution. And that sort of once again relates back to the whole optimal transport idea of you're transporting sort of what is known today to a potential model in the future, but you have all these potential models that you could select. So what is the worst case model? What is the best case model? And the area of robust finance sort of looks at that. Once you have a model, usually the model tells you something. So it can tell you, for example, the prices of financial contracts in the case of financial mathematics. And then those are the type of data that you can compare to actual real life data. So in particular, prices of financial contract exist on sort of various exchanges, people buy and sell these products. So the prices are out there, the information is out there, but the underlying model is not, right? So somehow we see the end product of the model and these are sort of grounded in reality. But in order to sort of work backwards and work out what is the underlying model involves the type of mathematics that we do. So we worked on a couple of different problems. One of the problems was motivated by robust finance, where essentially we had some ideas of the type of results that we want to prove in mind, and we try to work through the details. And sort of, as is with mathematical research, we've run into a lot of technical difficulties in terms of, challenges in terms of actually proving the results. But we have made some progress and we have some ideas of how to proceed forward. And at the same time, during these meetings, we sort of found some new interesting problems to look at that we didn't think of when we started. Face-to-face working environment really helps, and it's very different to working in correspondence or online. And it's really conducive to this process of not just working on problems, also the extra discussion that motivates additional problems to look at. So originally, when I did my PhD at Sydney, my main topic was essentially exploring how multi-agent games can be sort of featured in financial mathematics. Because mostly up to that point, the study of financial mathematics is about sort of buying and selling various assets, and that's usually a transaction between two parties. One of the questions I was interested in was, what if you have lots and lots of different parties involved in a financial contract? How would that make sense? How would that resolve itself? How do you even define such a scenario or a contract? And what is the mathematics needed to solve these kind of problems? And then sort of more recently, there are more and more work in the areas of using game theory in financial mathematics. In particular, one of the sort of topics that people are interested in is in terms of how the financial markets work. So essentially, when you read the news or you look something up online, you go, oh, okay, the stock market's indices is this value today, or the stock price is that number. These numbers come from the active sort of participation of the traders in the market. So people buying and selling things at various prices that determine these numbers that you see. So in itself, it's one giant game that's being played by a lot of different participants. So usually the word that we use, these are sort of main field games that involve infinitely many participants, whereas in reality, it's finite, but it's large enough so we can approximate it this way. But each market participant has their own little objectives and they contribute to the movement on the formulation of the prices. So that process of turning sort of this game from the perspective of individual traders and market participants to the modeling of the prices that you see itself, sort of that process itself involves game theory and financial mathematics. Obviously, there's a lot of probabilistic modeling involved in financial mathematics. And then typically when people think of probabilistic, they think that there's some sort of randomness. And then people like to use averages as a good way of explaining, the outcome of something. But as we know, sort of averages is a very simplistic view of what's going to happen in the future. And in terms of financial markets in particular, in the field of derivative pricing, so these are just the pricing of financial contracts, using averages is actually not the correct way to go about doing something. So it's sort of quite counterintuitive at first. So for example, if you have a financial contract that specifies you will either receive, let's say, $10 or $20 with 50-50 probability each, normally you think, okay, that's on average about $15, so that contract should worth the average of $15. But in the theory of derivative pricing, it gets a little bit more complicated, and it turns out that averaging is actually exactly the wrong thing to do. As is with financial mathematics, the goal of a lot of these studies or a lot of financial industries to provide or to come up with good models to explain what will happen in the future. So there's an interesting conundrum that I always explain that suppose you imagine in a universe or in a world or even a financial market where every person is using the wrong model. So they just decide for one day that we're going to come up with this obviously wrong model, but everyone will use it. Then somehow that wrong model becomes the correct model because those are exactly the people that determine the prices of everything. The numbers or the results or the figures are not entirely driven by just sort of the natural laws of the universe. It's more so driven by the actions of the people that's involved. So somehow if the people involved are behaving a certain way, even if it's the sort of irrational or incorrect way according to some measure, somehow that becomes the correct way. I think for me, being a mathematician, the part that sort of motivates me the most is still sort of finding and discovering and solving nice problems, first and foremost. I always enjoyed mathematics ever since I was very young. And then I always enjoy the aspect where you're sort of working on something difficult and then you find this very unexpected or surprising or nice but different ways that sort of very easily solve the problem that was previously somehow seemingly impossible. So that rush that you get sort of is very, very hard to replicate